or give anything in euros. Our objective in this chapter is to select a bearing. In order to select a bearing, we have to calculate something called catalog rating or rated load. Now we give it a simple C10. Now we said 10 is given as a probability of failure of 10%. Now calculate this rated load. We need to know how much load applied on the bearing, what is the desired life, and what is the rated life. Okay, type of bearing or type of rod, and also a load type. This is considering the reliability 90%. So AF is called load factor, and it reflects how the load, the load characteristic. I mean that the load is a stationary or steady, if we say, fluctuating, impulsive, smooth, ramp, etc. Okay, so this factor reflects the nature of the load, because during experiments inside the labs, the loads are steady, not pulsating. So if the load is impulsive, so in this case I have to consider that. FD is the load carried by the bearing. Okay, and LD is the life of bearing. So this is actually a design requirement. I'll put it DR, okay? So DR for design requirement, this is design requirement as well. So based on the design, the loads on the machine, you calculate how much reaction loads, etc. You get the loads on the system, and also the life of bearing is based on how much you need the bearing for that. LR also is called L10, and 10 here again, probability to failure. It is a constant parameter, constant. Who determines the value is the bearing manufacturer. So this is the test they do, the life based of the test they do. So we have two groups of life, 10 million cycle, okay, and 90 million cycle. Now, which group of bearings use a 90 million cycle is the tapered roller bearings. Those types of bearings who are good in carrying both thrust and radial. What about the others? The remaining, ball, cylindrical, they go with wind. No? Fine. Now, if we do and follow these steps and calculate the rated load, and go and open the catalogs and pick a bearing, we are picking a bearing with a reliability of 90%. It means our selected bearing may fail before reaching the desired life. There's a chance of 10% that the bearing fail before reaching the desired life. What if your design requirement asks you for higher reliability? So reliability, for example, 0.99. What do we have to do? Okay, so in this case, I need to recalculate the rated load, but considering the effective reliability. It's just like in fatigue failure, if you remember, when we used to calculate the endurance limit of a structure, we consider the effect of surface finish, effect of nature of load, bending or axial or torsion, the effect of temperature, and reliability was one of the factors. So, to incorporate the effect of reliability, we determine a factor, we call it XP. So, you can call this correction factor. So, reliability correction factor. So, how we define this correction factor? Now, when they test the bearing, they found out that they fall in a certain distribution. So, whenever you are targeting higher reliability, bearings will fail at certain points, and they can fit a certain distribution called wide distribution. So, the reliability is what you set, okay, is calculated using this formula based on the distribution. And those parameters, theta, x naught, and b, are what? The distribution parameters, okay? And they are fitted based on the experiment. So these parameters are based on statistical analysis. The unknown here, x, I'm representing there by xp, okay? So this is a correction factor for the reliability. Always the reliability should be known to you as a designer. Now, as we know from fatigue, whenever we look into higher reliability, the expected strength of the material is decreased. Okay? So the same thing here for life. Every time you are targeting higher reliability, your expectation for bearing life should be lower. Okay? So to achieve the same life, I need to utilize a bearing that has higher capacity. Come on? Right. So whenever the desired reliability is greater than 90%, we calculate the correction factor XP. So XP is calculated as follows: x naught plus theta minus x naught times ln 1 over RD. So what is RD? Simply the desired reliability. Okay, so this is again design what? Requirement. All to the power 1 over B. Okay. Now those 1, 2, 3 are based on bearing type, based on statistical analysis. So these values are tabulated values. The bearing manufacturer will be providing this in the catalog. Okay, so those parameters are not calculated. RD, reliability, is again design requirement, so you should know the value ahead of time. Right, where does this fit in this equation? C10 is equal application factor, desired load, times LD over LR, all divided by XP. Come on. So when we calculate XP, you'll notice that XP is always less than 1. So what happens to C10? If you want to increase the reliability, your bearing selection, you'll notice that capacity of the bearing must be higher. Any questions so far? Right. Let's see from where we can get those wide distribution parameters. Open, yes. Yes. You can, practically you can have a reliability of 1. You are running parallel systems. Okay, so when you have, let's say like a production line, and you want to, or a pump that is supplying a certain material to a production line, and you need to make sure that the supplied material is continuous form and no, there's no shutdown or cut away of the supply. What you do usually, you have a running of 2 or more systems in parallel. In case of one is shut down due to any reason, the others directly stopped. Okay, so that is when you try to achieve the reliability of 1 or 100%. Now the reliability of structures based on your design, you can select them with the reliability. When we talk about elements, you can select them with the reliability 90%, 95%, and 99%, etc. So every time you are targeting higher reliability, you have to pick the element with a larger capacity. Because although you are loading it with the lower forces, but because it has higher capacity, it's more reliable. Just like the trend before, people say, okay, to go buy Toyota rather than go by Hyundai. Huh? Why? Reputation of the car indicated that it has higher reliability. Huh? But not anymore today. Huh? All cars are almost the same. 5 years and put in the trash. Because manufacturers now, they don't look for reliability, they look for consumption. Toyota Cressida never failed. Huh? I remember we used to have an 82 Toyota Cressida when we used to travel in the desert across Saudi Arabia. And when you reach the borders, you have to wait for, before, people used to wait for 3, 4, 5 hours in the borders. It's too hot, everybody is shutting off their cars because temperature of the engine will increase. Okay, and we are sitting in the AC, cooling it down, engine temperature is normal, everything is normal. Because of the way that was the cars were built. So, but today manufacturers, no, they look for cheaper in order to simply have the consumers consume more. Tamam? So, for the Weibull distribution parameter, we extract them from table 11.6. Where this table is located, if you have the book, for those who have the book, it is at the end, 601, which is at the end of the chapter. Okay? Right. So, as you can notice, we have two manufacturers here. 1 and 2. 1, they are having a rated life of 90 million. So this is for which type of bearings? Tapered roller bearing. Now what about the rest of the bearings? We go with manufacturer 2. So cylindrical or ball bearing, we go with manufacturer number 2. So these are the values of X, naught, theta, and B utilized to calculate the correction factor for reliability. So whenever we look at reliability, you have to visit table 11-6. And you need to make sure that what type of bearing you are using. Are you using ball bearing or tapered roller bearing? So you pick the correctly the parameters. Come on? Any questions so far for the reliability part? Now, may I pick this? Seems it's simple. You 3-4 times one after one, and do the right thing, keep it upside down. Right. So let's discuss the reliability a little bit. Now, if you remember in electrical circuits from school, imagine you have multiple lights and they are connected in series. Okay, and this is your power source. What happens if one fused? All will shut down. Right? Now the same thing, we look into a mechanical system, like a gearbox, like a pump, a compressor. So any element inside the system fails, the entire system will not do the job correctly. So the same thing if you look at the bearing. So here is an example of a gearbox. This gearbox consists of only 2 stages. Okay? You have an input shaft, a driving gear driven, another driving driven. This is called counter shaft, which carries 2 gears. Okay? So we have a total of 3 shafts, a minimum number of bearings 6. Come on? So inside this gearbox we have 6 bearings. Now if any of those fail, can I still continue running the gearbox? The answer is no, because if one failed, it start to produce a noise and start to vibrate a lot, and this will ruin the gears, etc. Right? So it means we have a system of in series. One failing means the remain fail. Right. So how do we determine the reliability of a system? Because when you design, you don't design for individual elements. You design for the system. And you need to achieve that the entire system has a certain target reliability. Okay? Now, reliability of system in series is calculated as follows. If in the system there is n elements, so the reliability of the system is R1, times R2 times R3 till Rn. Okay, so it's a product of individual element reliability. Let's take an example of selecting the bearing with a reliability 90% for this particular gearbox. So if I assume that all the bearings were selected with the same reliability of 90%, they have 6 bearings, so the reliability of the set is 0.9 is individual reliability, multiplied by itself 6 times, so I take it to power 6. So what's the value is going to be?
0.53.
0.53. So the reliability of the system here is 50% almost. So there's a 50% chance that the entire system failed. Okay. That's why we always look for a higher reliability. So if you believe 90% is a good choice for individual reliability, no. The answer is no. What if you want to have the set reliability is 90%? You just simply reverse this formula. So if this is 0.9, will equal individual reliability to power 6. So from here, RD is equal to 0.9 to power 1 over 6. Can anybody calculate that? Exchange, right? Or do you have to go for a lunch? 0.98. So you can see individual reliability 98% for each bearing to achieve a set reliability of 0.9. So it depends on number of elements again, and the individual reliability of individual elements.
Doctor,
Yes.
you mean for every part the reliability is 98%?
This is only for the bearings. So each bearing should have a minimum reliability of 98%.
In this case?
In this case, a gearbox of 6 bearings. Sorry?
That's
Difficult to achieve?
this is okay. Not like 0.98.
Yeah, 0.98. This is to achieve 90%. What about if you want it to be 95?
Just
Entire set? Can anybody calculate? Definitely this will be bigger than 0.98. Huh? 0.99, huh? And so on. Yes? The calculation of, I forget the formula for reliability of parallel system, but it is like this. It is the summation of the difference. I think so. Anybody work with the reliability people? It's the summation of the difference. So 1 minus the reliability of the first bearing, and all divided by something.
it's multiplication.
Is it? You can multiply them together, it will always be this number.
Doesn't make sense. Not it.
No, it's not multiplication. I think here it is. I forget the equation. I'll inshallah on Thursday I'll bring you that equation. So I record this equation somewhere. So where it's a kind of addition, subtraction, and addition to get the reliability. You cannot see from here. So what is the formula? For parallel systems?
Must be bigger summation.
It has summation, something is summation. I don't remember the formula.
As you said, you can see is one component failed, the entire system failed.
Yeah.
So that's-
So you have when you have them parallel, it's kind of addition. I don't remember exactly. Maybe 1 minus the sum of them, something like that. Fine. Okay, let's do this exercise to see how we apply formulas here. for bearing selection. One thing before I move on. Yeah, we can do that. Right. So this example is asking you to select a ball bearing with a design life of 25 kilo-hours, speed of 350 RPM. Radial load is given, and the application factor is given. Okay, and then now I'll show you from where you can look into the application factors. The reliability goal is 95%. He's asking you to select the bearing, so you need to calculate C10. Let's start with the setting the equation. So C10 is equal to the application factors times the load times, I'll give you a new term, XT over XP, power 1 over. XT is simply LD over L10. So don't worry about the same. Now we start with the application factor. From where I can locate the application factor, we have table 11.5. 11.5, table 11.5 provide the range of load factor for different applications. So for example, precision gearing means the gears were produced in high quality, dimension and tolerances are very tight, etc. So here we expect that this gearbox is running smoothly without vibration and excessive vibration. So you can see the load factor is from 1 to 1.1. For commercial gears, usually the quality of gears are low or average. Tolerances are quite large, and therefore we expect to have some pulsating load during meshing of the gears. So you can see the factor is from 1.1 to 1.3. Where you have poor sealing, 1.2. When you have no impact, you can go back from 1 to 1.2. If there's a light impact, 1.2 to 1.5. Moderate impact loads, 1.5 to 3. Now, someone will say, we have a range. Which value you pick? If you are conservative, your phone is not conservative. Put it down.
Go with higher load factor.
If you are not conservative,
Low.
low. And if you are conservative, you go with higher load factors. Tamam? So in our example, we said that the application factor is equal to 1.2. So we don't bother ourselves. That's right. Now for the life, calculate the life. The life were given in hours, kilo-hours. So to change them into cycles, I take the life in hours, multiply by 60, and then multiply by the rotational speed. So I'm converting the life from hours into cycles. Now he said 25 kilo-hours, so don't forget the 1,000, okay? Times 60 times the rotation speed, 350 RPM. Yalla, so give me the value. Now what is L10? Can anybody tell me L10 is equal to what? What is L10? What does parameter represent? Yeah. Rated life. So rated life for ball bearing is 1 million. Good. 5. Now for the desired load, you give me it is 2.5 kilonewton, or okay? 2.5 kilonewton. What is remaining? A is equal to what? 3. Remember A, 3 for ball, and for the others, 10 over Okay?
Again, the design, the catalog life, from where you get it.
Because it's ball bearing. Okay? Tamam? And this one was given. Okay, now we calculate XP. What is our reliability goal? 95. So XP is equal to X naught plus theta minus X naught times ln 1 over 0.95 to power 1 over B. From where I can get those X naught, theta, and B? Table? 11.6. Let's find it. So in 11.6, which manufacturer we have to use? 2. Manufacturer 2. So the value for those parameters, so XB is equal to 0.02 plus 4.459 minus 0.02 times 1 ln 1 over 0.95. From where we got the desired reliability? It's a design requirement, so it's a given in the problem. The power 1 over 1.48. 3. يلا شباب. Give me the value. LD is equal to
525 million.
this is LD or XD?
Rudy.
Million. And XD is going to be simply
XB 0.619.
0.619.
619.
And for XD is going to be 525. Okay, can you now calculate C10? 1.2 times 2.5 times 525 over 0.619 power 1 over
28.4.
28.4 what? What's the unit? What's the unit? Kilonewton. Excellent. Kilonewton. Rated load. Load. Okay? Fine. So now we have the rated load. The idea is now you open the catalog and look for a bearing that has a capacity of 28.4 or greater. Huh? Yeah, no, if you go with lower, what would happen? I will not say fail. Your reliability become low. Not necessary to fail. Reliability will be low. And if you want to still have the reliability the same, you need to underestimate or reduce your estimation for the life. Any question? Okay. Second part of the lecture is continue with the ball bearing, but now we would like to look into a different aspect. Now we said the ball bearing, they have a capability to carry combined load, radial and thrust. Okay? Now, the catalog's rating are based on pure radial load. The ratings based on pure radial load. How can I select the bearing if I have a combined load? Can I ignore that there's a thrust load? Not possible. Can I find the resultant load and say that this is the load applied? Also no. Okay, so resultant load, no. Big no. Okay, so what we have to do is to find something called equivalent load. So what do you mean by equivalent load? It's simply a radial load that cause the same damage of those as when they are combined. Simple example. Imagine you have a bearing loaded with 10 kilonewton force, radial force, pure radial force. After a certain period of life, you open it, you see a certain amount of damage. Now, the same amount of damage is caused by having combined load of, let's say, 7 radial and 2 thrust. Okay, so this is the idea of the equivalent load. We try to find how much radial load can cause the same damage of a combined load. So today we will learn how to calculate the equivalent load. Right. Is the procedure we are learning today applies to all type of bearings? All type or specific type? It's only applied to ball bearings. What about cylindrical roller bearing? Do we have a different technique for equivalent load? There is no thrust load, so only radial load. So there is nothing called equivalent load in cylindrical roller bearings. Okay, so be careful about this. Whenever you have cylindrical roller bearing, there is no thrust load at all. Okay, fine. So let's start. So as I said, ball bearing can carry a combined load. Catalog ratings are based on radial load, pure radial load. I need to find a solution to select from that catalog while I'm having to combine load. Right. So the process is followed. Again, we go back to statistical analysis based on manufacturer. Then manufacturer will think about having combined load. So they will give you some data similar to the plot in front of you. So what does data present? This data try to reflect the effect of thrust load on the equivalent load. So the x-axis here is the ratio between axial load and radial load. Okay? The y-axis is the ratio of equivalent load to radial load. Now if you look at the data point represent the experiment. So the data points from 0 radial axial load or thrust load up to a certain value, you can see that there's no difference between the equivalent load and the radial load. So it means that the axial load is not contributing on the development of failure inside the bearing. It's just like the bearing, but it's not seeing that thrust load, it's not affecting the bearing on its life or in its fatigue life. Tamam?
Don't consider it? Or?
So you don't consider it. Now, but after a certain ratio of thrust load to radial load, you can see there is a trend that can be considered linear. That this trend shows that the equivalent load is becoming greater than the radial load. Why it's becoming greater? Because thrust load is contributing now in the damage of the bearing. So the idea when we want to calculate the equivalent load is we need to know first, are we in this zone or this zone? Then, if we are in this zone, we calculate the equivalent load. Following this formula, it's simply a linear equation. So I need the slope, intersection with the y-axis, and that's it. Right. So how we calculate the equivalent load? Equivalent load is calculated using this formula. Fe is equal to VFR. This is FA over VFR is less than a value E. So this is case 1. Case 2, if A over B F R is greater than value E, in this case equivalent load will equal B F R times X plus F A times Y. So Y is the slope of the line and X is the intersection.
If A is equal to the process.
FA is the thrust load, this is a thrust load, and this is radial load. Again, those two are design requirements, remember, based on the design. Loads on the shaft, etc. Okay? Fine. What is V? V is related to the way the bearing is running. Now, if I have a rotating shaft, which part of the bearing rotates? Inner ring. تليفونات يا شباب الطاولة. Inner ring. Okay? Fine. If I have an axle and wheel, the outer ring is rotating. Fine. Is there any difference? Speed of rotation? No, I can make the outer ring rotate at 1000 RPM and then a ring rotate at 1000 RPM. But what would change?
Contact. Is this some point of the contact?
What point of contact? There's something before the physical property before the point of contact. Velocity. Now this is your roller, huh? This is center of the bearing. If the inner ring is rotating, what is the velocity here? No, here. Says equal to, V is equal to omega times R. I'll go make it R1 or Ri. So, what if the outer ring is rotating? What is the, we'll draw another one here. What is the velocity here?
WR.
Outer minus
No. It is simply V equals to omega R. Out.
Okay.
And remember, those 2 points are the ones driving the roller to roll. So, and the other point, the contact is 0. So the speed of the rollers will change. Therefore, you have to do kind of correction because the laboratory test is based on inner ring rotation. So V has 2 values. V either equals to 1 if, what? What do you think?
Out.
V equals to 1, not velocity, V the parameter here. If the inner ring is rotating, because we're having the same results as the experiment. V is equal to 1.2 if the outer ring is rotating. Come on? Now this applies to all types of bearing except the self-aligning. Come on? So self-aligning bearing, they are excluded. Anybody know the reason? No. The radius is not fixed. The radius is not fixed. Because it's self-aligning bearing, it tilt. Okay? And usually self-aligning bearing are utilized in shaft rotation. Okay? We don't use self-aligning bearing for axle. For axle we don't use because the axle is not rotating, so we don't care. There's no alignment issue. Huh? Fine. Tamam? So that is for the calculating the equipment. Now, Shabab, whenever equivalent load is smaller than the radial load, yani for any reason, you are calculating and you notice yani you did a mistake, and instead of assuming that there is no effective thrust load, you consider the effective thrust load. and you calculated the equivalent load, you will find out that simply the equivalent load is less than the radial load. Okay, so it doesn't make sense. So what you have to do, you recheck. Okay, first thing. Second thing, if you checked and found that everything is correct, you make the equivalent load equals to the radial load. Tamam? Okay. We'll do one exercise. Hopefully we have sufficient time. What time is it? 45. Meaning I have to run for. I will skip this part, selection, and I will go to introducing this problem. Next class we'll go to the selection. Right. So in this problem, he's asking us to select a ball bearing for industrial machine intended for continuous one shift, 8 hours a day operation at 1,800 RPM. Radial load and thrust loads are given. The machine operates with a light to moderate impact load. So this is for the application factor. Desired reliability 95%. Now, one issue with the live. Okay, sometimes the customer who's asking you to design the machine doesn't have a specific life, but he tell you how the machine is going to be utilized. Is it going to be continuous working condition, or is it going to be simply utilized a few times a day? Is it working for one shift or two shifts a day, and so on? So, if he gives you information like these, like for example, he's saying that it's going to be used for one shift in a continuous fashion during the shift. So, in this particular case, we go and consult the recommendation. So we have a table for recommended life. So table 11.4 gives you the application and the recommended life. Recommended life here is in kilo hours. Tamam? So let's see, for our case in the problem, he's saying 8 hours a day and in a continuous fashion. Tamam? So the best one is machine for 8 hours service that are fully utilized. Continuous, it means along the 8 hours, it is working. Okay? Sometimes they are not fully utilized. So tell you 8 hours service that are not always fully utilized. For example, a lathe machine in a workshop, but it's not a production workshop like the workshop we have here in our building 1. The machines there are not fully utilized. They are not running all through the 8 hours a day. The technician uses them maybe a couple of hours a day, then they move to another machine, use it for another 2 hours, and so on and so forth. Okay, so this is not fully utilized. But if you want it to be fully utilized 24 hours, for example, look at the life. Continuous 24-hour service from 50 to 60,000 hours. Now, this is with not high importance. But if a machine that is extreme importance, you design it to live from 100 to 200 hours. Okay, kilo hours. So this table helps you in determining the life. Now let's go back to our problem.
Does it mention here that it's fully utilized?
Continuous means fully utilized. Yeah. So in this particular problem, so I'll just go over the inputs, and then we'll let you try to do it yourself. So please take a picture of the statement and try to solve it at home. So he said it is for a continuous operation for 8 hours a day, and the recommendation was from 20 to 30 kilo hours. Okay? So this is the range of operation. He said also that this is the life. Okay? For application factor, he said that the load is from light to moderate impact. If I go to the table, light impact loads are, the factor for them is from 1.2 to 1.5. Moderate impact from 1.5 to 3. So if I'm between light and moderate, suitable factor is 1.5. Now he's asking me to select a bearing. So select a bearing, you have to calculate the rated load. So application factor now is known. equivalent load is unknown. Then I have XD over XB power 1 over B. Now, based on this, I can calculate XD. And based on the reliability goal, I can find XB. A is known because it's a ball bearing. What is remaining is FB. And I think your time is finished, sir. And next class, we'll tell you how you can calculate FE.
Safety from the table. So you say
Yeah, this is the line. From continuous to 20 to 30 kilohertz. If you open the table, for 8-hour service, continuous from 20 to 30 kilohertz. We'll pick a value from that. It's just like always. If you are conservative, you go with a high, and conservative, you go with a low.